Hello everyone, this is Vijetha, Associate Professor in the Department of ECE from MLR Institute of Technology. Today I would like to have a talk on DC characteristics of an op-amp from linear and digital integrated circuits. The contents which I want to discuss here are why we are studying DC characteristics for an op-amp and what are the different types of DC characteristics and how to nullify the offset. These are the three topics which I want to discuss here. Why we are going with the DC characteristics. The first content which we want to discuss is why we are going with the DC characteristics. Ideal operational amplifier draws no current from the signal source and it is independent of temperature variation. It doesn't depend upon the temperature variations and it doesn't draws no current. It doesn't draws current from the ideal operational amplifier. But practical op-amp affected by the environment and process variation. So, the current taken from the source into the input of an op-amp responds differently to the input voltage and current. And this is due to mismatch among the transistors. This leads to study the non-ideal DC characteristics for an op-amp. So, the next content is what are the different types of DC characteristics. So, the non-ideal DC characteristics of op-amp are input bias current, input offset current and input offset voltage, thermal drift. These are the four types of DC characteristics. The first one is input bias current. It is defined as the average of the current that flows into inverting and non-inverting input terminals. The positive terminal which we are seeing here is a non-inverting input terminal and the negative terminal which we are seeing here is a inverting input terminal. So, input bias current IB is given as average of IB1 plus IB2 which you can given as IB1 plus IB2 divided by 2. In the circuit, your positive terminal, this non-inverting terminal is directly connected to the ground and inverting terminal is connected to the resistor and which is connected through the input voltage Vi. But actually your output voltage should be equals to 0 because the input voltage which we are given to a non-inverting terminal is 0. The input voltage which we are giving to the inverting terminal is 0 and we are not giving any input to the non-inverting terminal. So, your output should be 0. But because of the offset, your output voltage is given as IB2 into RF. To nullify this output, what you need to do? So, I am just including a R compensator to reduce or to cancel the offset. So, I have connected, see in this circuit, the positive terminal is connected to a ground through a R compensator resistor and the negative terminal is connected to a Vin through a R1 resistor. And the feedback RF is connected from R1 towards the output voltage. So, you need to choose the proper R compensator to make your output voltage 0 or we can say that to nullify or to cancel the offset. How you need to choose the R compensator? What should be the value for R compensator? The question here. So, now what I am doing here is I am applying a KVL across this loop and I am writing it as a minus V compensator plus the voltage across this is 0. So, V compensator plus 0 plus this is minus V compensator 0 and here it is V2 which will be equals to V0. To nullify, that is to make V0 is equals to 0, you need to choose V2 as plus V compensator. So, you need to choose proper V compensator to make V0 is equals to 0. So, if you want to choose V compensator properly, you need to choose a proper R compensator. So, what I am doing here is now applying a KCL across this node. I am writing this as the current entering to the node is I1 and the current entering to the node from this arm is I2 I1 plus I2 is equals to the current leaving through this arm is IB2, which you can write it as IB2. So, I compensator I1 can be given as C by using a virtual ground concept. The voltage across this is V compensator. So, the voltage across here will also be equals to V compensator. So, your I1 can be given as V compensator divided by R1, and I2 is given as we need to get V0 is equals to 0, you need to choose V2 is equal to V compensator. So, your I2 can be given as V compensator divided by RF, which is equals to IB2. So, you can write the IB2 is equals to V compensator into 1 by R1 plus 1 by RF. Let us assume that IB1 is equals to IB2. We derived IB2 as V compensator into 1 by R1 plus 1 by RF. But IB1 can be given as V compensator divided by R compensator. So, IB1 can be given as V compensator divided by R compensator, and IB2 is V compensator into 1 by R1 plus 1 by RF. If you get cancels this V compensator on both the sides, you can write 1 by R compensator is equals to 1 by R1 plus 1 by RF. So, we can say that R compensator should be chosen as R1 parallel with RF. So, input bias current is defined as the average of IB1 plus IB2, but actually as we are connecting the input voltage to a inverting terminal, you need to get your output voltage 0, but here you are not getting output voltage 0 because of the offset. So, to make V0 is equals to 0, you need to choose a proper R compensator, and which should be equals to R1 parallel with RF. The second DC characteristics is input offset current. Input offset current is defined as the difference between the magnitude of IB1 and IB2. That is, IOS is defined as input offset current, which is defined as the difference between the magnitudes of IB1 and IB2. Here, to find the effect, see, in this circuit helps us to find out the effect of IOS on V0. Here, just by applying a KVL across this, you can write minus V compensator plus V2 is equals to V0. So, you can write V0 as V2 minus V compensator. But V2 can be given as the current allowing through this arm is I2. V2 can be given as I2 into RF minus V compensator, and V compensator also can be given as the arm here, the current which is flowing here is IB1. So, V0 can be given as I2 RF minus V compensator can be given as IB1 into R compensator. Now, we need to know what is I2. So, to determine I2, what I am doing here is I am applying a KCL across this. So, KCL across this. So, I1 plus I2 is equals to IB2. You can write, we want I2. So, I2 can be given as, from this equation, I2 can be given as I2 is equals to IB2 minus I1. What is IB2 here? IB2 is the current which is flowing through a inverting terminal. So, which you can keep IB2 as it is, and I1 can be given as V compensator by R1, as the voltage across this is V compensator because of the virtual ground concept. We can assume V compensator here also. So, I1 can be given as V compensator divided by R1. And now, coming to this V compensator, you can write V compensator here from this arm. V compensator can be given as IB1 into R compensator. So, by substituting V compensator as IB1 into R compensator, we can write I2 is equals to now IB2 minus IB1 into R compensator divided by R1. If you can substitute the I2 in this equation, you can write V0 is equals to I2 as IB2 minus IB1 into R compensator divided by R1 minus IB1 into R compensator. If you can simplify this expression, finally we can get V0 is equals to RF into magnitude of IB2 minus magnitude of IB1. Simply we can write V0 is equals to RF into I. So to nullify your output voltage to 0, we can have V0 is equals to RF into I, where I is input offset current, which you can write it as IOS, which is the difference between the current, magnitude of the currents for the inverting and non-inverting terminals. The third one is input offset voltage. Input offset voltage is defined with the VOS, and it is defined as a differential input voltage that exists between the inverting and non-inverting terminal of an op-amp. Here, if you can apply a voltage divide rule over here, you can write VA is equals to V0 into R1 plus RF divided by R1. So you can write VA is equals to V0 into 1 plus RF by R1. Or V0 can be given as VA into R1 divided by R1 plus RF. So V0 can be given as VA into 1 plus R1 by RF. But VOS voltage, offset voltage is given as VA minus VI, where VI is equals to 0. So we can write V0 is equals to VA. VOS is equals to 0 minus VA, that is actually the input voltage at non-inverting terminal minus the inverting terminal. So the input voltage at non-inverting terminal is 0 volts minus the voltage across the inverting terminal is VA. So 0 minus VA, which you can write as VA. So VA can be given as V0 into 1 plus RF by R1. Or we can say that V0 is equals to 1 plus RF by R1 into VOS. VOS is a difference between the input voltages, magnitude difference between the two input voltages. So total offset voltage is given as 1 plus RF by R1 into VOS plus RF into IOS, which we have derived in input offset current. So total offset voltage is given as VOT is equals to 1 plus R1 by RF into VOS plus RF into IOS. And the fourth DC characteristics is thermal drift. It was assumed that VOS, that is input offset voltage, bias current and input offset current are constants for a given op-amp. But these VOS, IB and IOS changes with respect to time, with respect to supply and with respect to temperature. The change in the temperature causes the most serious variation in VOS, IB and IOS. The term thermal drift is used to identify such changes, and it is defined as the average rate of change of input. Delta VOS by delta T, the change in the VOS with respect to change in the temperature is given with delta VOS by delta VT, and the units which can be used here is microvolts per centigrades. And delta IOS by delta T, that is input offset current, is changing with respect to temperature, picoamps per centigrades, and input bias current changing with temperature, given with picoamps per centigrades. So these three components, that is offset current, offset voltage and bias current, changes with respect to temperature, changes with respect to supply voltage and changes with respect to time. So these are the four DC characteristics. Coming to summary. Here in this video, we have discussed four different types of DC characteristics. Offset voltage, input offset current, input bias current, and thermal drift. These are the four DC characteristics which we have determined here. Total offset voltage is given with V0 into VOS into 1 plus RF by R1 in plus IOS into RF. And input offset current is defined as IOS into RF. And input bias current is defined as the magnitude, the average of IB1 plus IB2. That is, IB1 is the input current which you are giving for a inverting terminal, and IB2 is the input current which you are giving for a non-inverting terminal. The average of these currents is nothing but IB, that is bias current. And the proper choosing of R compensator is important parameter, which is given with R1 parallel with RF to nullify the offset. So these are the four different types of DC characteristics which we have determined in this lecture. Thank you.